Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 97, Coulomb's law. Let's start at the beginning. This is a law about electricity and magnetism, but more specifically about electricity or electric charge. And I have a piece of silk here, and if I rub this piece of amber on the silk, and then hold it up to these little bits of paper here. You see that? So what is it that drew the paper up to the amber? Well, this is what we are exploring. This is electric charge, okay, and the electric force, so specifically the electrostatic force. I can do the same thing with a glass rod, and I'll just direct your attention to the electroscope, which consists of it's a flask that's closed off by a rubber stopper on the top. Going through the rubber stopper is a copper wire. At the end of the copper wire is attached two aluminum foil leaves, okay? And at the top of the copper wire coming out of the flask is a little bit of coiled wire. That's just to increase the surface area of the wire. And so if I rub this glass rod on the silk, just like I did the amber before, and I bring the glass rod near the coils, you see that? So why is it that the coils are moving apart? Or excuse me, why is it that the leaves are moving apart? You can see that the closer I get, the farther apart the leaves move. You see that? On the one hand, I've shown you an electric attraction, and with the electroscope, I showed you electric repulsion, where the leaves were repelling each other, away from each other. So that is kind of a different kind of force than what we're used to, right? Don't know what all this stuff down here is. Let me point out that the word electron, from which electricity and electric are derived, comes from the Greek word that means amber. So electron means amber in Greek. It's because the first experiment, like what I showed you with the amber attracting the little bits of paper, were actually done by Thales of Miletus, sometimes pronounced Thales of Miletus, over 2,500 years ago, so a really long time ago. It's the first person to do that, at least recorded having done it, and made that observation about this bizarre property of amber. Okay? And so now we know what's going on, right? The rubbing of the amber on the silk, what's happening there? It's an effect known as the triboelectric effect. It's where electrons from the amber are, well, actually it's electrons from the amber are rubbed off onto the silk, giving the amber a net positive charge. Okay? We'll talk more about what it does to both the leaves in the electroscope and the little bits of paper towards the end of the lesson. But the reason we call the electron an electron, which is the carrier of charge, as we now know that we have the atomic theory, is because it was named after this little rock, amber. It's actually it's a kind of a petrified resin. Some people would say tree sap, but it's a tree resin. I don't know if it always comes from trees, maybe other plants, but anyways. So let's just briefly summarize what we saw. We saw that the force could either be attractive or repulsive, right? It seemed to have some dependence on the distance, right? And if we were really careful about it, we might be able to, like, rub it more and put more charge on and see that the more charge that was put on the rod, the larger the force is, okay? So it seems to be proportional to the charge, inversely proportional to the distance somehow, right? Such that if it's as you move it farther away, the force drops off rather dramatically. And it seems to be able to switch between attractive and repulsive somehow. Okay, so I'm going to kind of just cut to the chase, and I'm going to show you what Coulomb's law is. But first, let me remind you of Newton's law of universal gravitation. And I'll put that over here, right? So this is, I'm just going to write Newton, and I'll write it F sub g. I'm also going to write it as a vector, meaning that it has both a magnitude and a direction. And you'll recall this is equal to a constant, big G, times the product of the masses divided by the square, right, like this. The modulus squared, or the square of the distance between them, and it's directed in the direction of the force is along the line that connects the two bodies, right? And so we denote that with a little vector like this, We'll call it R12, and we put a hat on it. And the reason the hat is there is because it means it's normalized, okay? It means that the length of that vector is equal to 1, okay? And I'll show you later why that matters and how it can be different. So that's Newton's law of gravitation. You remember that, right? And if we look at it, we're like, okay, well, we've got our mass. We don't see any way this can become negative, right? Yes. Because mass, as you recall from one of our earliest lectures, I forget what number it was, I should have looked that up, we define it in terms of the acceleration between bodies, right? And it's always a positive quantity, okay? There's no such thing as a negative mass. And so G is a positive constant, and down here in the denominator we have a quantity which is squared, which has to be positive, right? I suppose you could imagine putting in, you know, imaginary distances or something like that, such that when you square them, the square of I is -1, right? But aside from that, there doesn't seem to be any way to get an attractive force out of this, okay? Now let me show you Coulomb's law. I hope I'm spelling his name right. Coulomb's law. And I don't actually know what year this discovery by Coulomb was made. If somebody knows the year, they can post it in the comments. That would be helpful. But it was after Newton, okay? So Coulomb knew about this, okay? And in fact, the experimental apparatus that he used to show this was the same experimental apparatus they used to measure the mass of the Earth, okay? The Cavendish experiment. So let me write down Coulomb's law. I'm going to write it like this. I should have done it. Well, here I wrote FG. I'll just write F. Well, I think it's enough that it's here. It's also a vector. The force between body 1 and 2, or 1 acting on 2, rather, is a constant. We'll call it K, times the charge of 1 times the charge of 2. I'm going to use my little curly Q's. That way you can see they're a Q and not a 9, okay? So it's Q sub 1, Q sub 2, divided by the same R12 squared, the distance between them squared, times this vector R12, okay? So, looks pretty similar, right? If you look back at the Cavendish experiment, right, this is where they took 2 large masses and then they suspended 2 smaller masses on something that looked like a clothes hanger almost, right? And it was hung from a ceiling with a wire, and this wire had a torsion in it, right? This rotating, it's like a spring in the rotational direction, right? Such that if you try to rotate this way, it pushed back with increasing force the more you rotated it, right? It's like a spring, it would pop back, okay? And so using the knowledge of that wire and the knowledge of the masses involved, they were able to basically figure out what this gravitational constant was, and also verify this R squared, this inverse square law dependence on the distance between the objects, okay? But you can use the same thing, but with metal spheres, put charges on them, okay? And very similar to what we did here with the glass rod and the amber, right? You can transfer charge to an electric body. If it's insulated, then you remove it, the charge stays. And they can do the Cavendish experiment to verify this 1/r squared law and also get this value K, the constant. I don't know if they call it Coulomb's constant or not, but it's 9 times 10 to the 9. I can summarize it here. K is 9 times 10 to the 9 Newton times meter squared per Coulomb squared. Coulomb is the measure of electric charge, okay? And I'm not going to go into detail on what the formal definition of 1 Coulomb is, because it has more to do with electricity, right? The flowing of, right? I think you understand what I'm talking about? Electric circuits, and we haven't gotten to that yet, so we'll talk about that definition later. But first, let's see if we can understand this repulsive. Let's see if we can understand this repulsive force versus attractive force, okay? So if I make a little table here, Q1, Q2, force, and just a description of it, right? So I'll make a table of values here, okay? If Q1 is positive, right, and Q2 is positive, then when we multiply 2 positive numbers times each other, we get a positive number, right? And so that will be a positive number for the force, which would be what we call repel. Okay? If one of the charges is positive and one of the charges is negative, what happens when you multiply a positive number times a negative number? It becomes negative. So the force is now negative. This is what we would call attract. This is the key thing that we could not do with masses, right? Because masses can't be negative, right? Alternatively, we could have the first charge be negative and the second charge be positive, which would still give us a negative force, and we would call that attract. And finally, if both charges were negative, a negative times a negative is a positive, making the force positive, and this would again be repel. So there is the behavior. It's explained by the bipolar. Is that the right term? It sounds like a disease. The bipolar nature of charge. It can have two signs, positive or negative, right? Charge can. Okay. Excuse me. So we see that the charge having two different values is what can explain the existence of these attractive and repulsive forces. And it was actually Benjamin Franklin, the American statesman, that hypothesized this notion. Okay, so does that make sense on understanding how it is that this force law can explain that we might see attractive forces as well as repulsive forces? I don't know if is that the right word, repulsive forces? Forces that repel, right? Does that make sense? Yes? So let me just spend a minute now talking about the vector nature of this, okay? Because this can get confusing for people sometimes. So what I'm going to do, I'm just going to do it in 2 dimensions to start with, because I think it's a little bit easier. So if these are my 2 spatial dimensions, we'll call this x, we'll call this y, right? And I would put, say, one charge, call it q1, right here at the location 1, 1. And I put another charge, let's say, I want to make it easier to get. Put it right there. And we need to draw a line from the origin here. And this will be Q2, located at 2, 3. Okay? Do you understand these coordinates as I've put them in? You go over 1 and you go up 1, you get it at Q1. I promised to use curly tails on these Q's, and I didn't live up to that. And for the second charge, it's located at 2, 3, so I go over 2 and up 3. Okay? And we can describe each of those by a vector, right? I'll call this vector R1, okay? I'll put a hat on it because it has a direction, right? And this is a vector R2, not a hat, but a line over the top. And that has a line over the top as well because it's a vector headed in that direction. It has a magnitude, though. We can write that out, right? How do we write that? Well, we would write R1 is equal to, the convention is the x direction, we use the I hat unit vector. So it's I and j, right? This is the I direction, this is the j direction. The little I hat is a unit vector in the x direction with a magnitude of 1. Okay? So it would be represented by a point at 1, 0. Okay? And the j unit vector would be located, you could draw it as a vector between the point 0, 0 and 0, 1. Okay? And so R1 you can write as, well, it's just I hat plus j hat because it's both 1 in that, right? The components. And then R2 we can write as, well, it's 2 in the x direction, so it would be 2 I hat, and it's 3 in the y direction, so 3 j hat. Yes? You probably remember this from the little bit of vector stuff that we did last semester, okay? That's all that is saying. So it's writing these different components, right? Yeah. Now you probably also remember that this, I'll just freehand it, hope it works out well. There, not bad. This I'm going to call R12, okay? What is that? Well, that is the difference between these 2 vectors, right? Using the parallelogram rule, right? So R12 is equal to, well, actually I'll call it R21 just to be consistent with what's happening here. R21 is R2 minus R1. Okay? Now how do we add and subtract vectors? We just do it component-wise. So what is this equal to? Well, this is equal to R2, which is 2I plus 3j minus R1, which is just ij. So minus I hat minus j hat, right? Since we do it component-wise, we have to combine these components. We can add the i's, right? So we have 2 minus 1 is just 1, so I'll just take that away. And then we add the j's. 3j minus j is plus 2j, right? So 2j. So there we have it. This vector, R21, which is the difference between these two vectors, right? That's the distance between the two charges. That's the direction of the force, right? So if I'm asking what is the force on this charge Q2, well, it's in this direction, the line that connects Q1 and Q2. That's the direction of it, and this is how we write it, okay? So how do we put it into this Coulomb's law business, right? So the force between 1, 2 will be equal to the K and the Q1 and the Q2. They're both positive, let's say, times, or really divided by this R12 squared. So how do we square this, right? Well, that's just the magnitude of it, right? And so the magnitude of R21, right, is equal to the square root of the x component, right? So 1 squared plus the y component, 2 squared. So that's equal to the square root of 5, okay? That's the magnitude of this vector. That's its length. So if I were to get my ruler out and measure it, it would be the square root of 5 long, all right? But we're supposed to divide by the square of that, right? Because it says R12 squared. So we square this magnitude, that's 5, right? So we get 5. You see that? And we need to multiply times this unit vector. Well, a unit vector is this vector R21, right? But it's normalized, meaning that its magnitude is 1, such that if I were to do this operation again with this vector, I would, instead of getting a square root of 5, I would just get 1. So I can take this vector, R21, right, and divide it by the square root of 5. And if I were to take the magnitude, it would now be equal to just 1. Because I know if I square I plus 2j, I'm going to get the square root of 5. So in order for it to be 1, I have to divide it by the square root of 5. Do you understand? So this part right here, r hat, right? You see it? Good? Yes? This I write like this. I write r, which is I plus 2j, but I have to divide the whole thing by the square root of 5. Okay? Now the reason I showed this to you is A, in the problem sets, there was a problem that involves vector stuff, and you'll need to be able to work with it, so this will be a good reminder of that. And B, because it's often written, Coulomb's law is often written a little bit differently. Okay, because look at this. If I were to move this square root of 5 over here, which is not a big deal, right? I just take this away, right? Move it over here, square root of 5, and rewrite this equation, but in a general form, I could say it's equal to, it looks like it's K times Q1. Keep forgetting to put the tails on my Q's so that you know they're not 9s. Q1 times Q2 divided by, well, 5 square root of 5. That's not quite R12 squared, right? It's not the magnitude squared. It looks like it's the magnitude cubed, right? Because the magnitude, R12, is just square root of 5. Square root of 5 squared is 5. And the square root of 5 cubed, that's square root of 5 times the square root of 5 times the square root of 5, is 5 square root of 5, right? So this could be written as R12 cubed, okay? See that? And then what's left? We're just left with this I plus 2j. Well, that's just R21, right? R21, but it's not normalized, so it's just the vector, okay? So a lot of times you'll see Coulomb's law written as with a non-normalized vector, in which case in the denominator you're going to see a cube. Same thing with gravity. Sometimes you'll see gravity written that way as well. And so whenever you see that, don't be alarmed that you misunderstood the law. It really is proportional to the square of the distances. It's inversely proportional to the square of the distances that separate the two bodies. Okay? It's just that depending on whether you use a unit vector or a regular old vector, right? You may have a cube in the denominator. Okay? When you do, that means you have to multiply this times this vector, because when you do that, right, this is some quantity, right? I keep missing the order up. I meant this to be R21. There, that's better. You can kind of see it's a little bit like you've got R21 up here and R21 cubed in the denominator. If I were to cancel those out, I just end up with just an R21 squared, right? You can think of it that way, but it's not really correct. But that's the idea, though. So just be aware of that. Sometimes you'll see it where you have the cube of the distance that separates them in the denominator. And when you do, that means that instead of using the unit vector, right, you'll use the regular vector, just the difference between this point here, something that doesn't have a magnitude of 1, okay? Let's talk about the strength of this thing, okay? Because I want to talk about another property of Coulomb's law that's not really in Coulomb's law, but it's something that we know now, right? And that is that charge, unlike mass, right, is quantized, right? It comes in little chunks. Now, mass does to a degree, okay? But let me explain why we don't think of it that way. When we think of gravity, right, what do we normally think of? We think of planets, maybe a space station orbiting a planet or a planet orbiting a star, right? And stars and planets and even satellites are made up of lots of stuff, right? And it's so much stuff that it's kind of the discrete nature of the stuff that it's made out of is irrelevant, okay? Because it's a huge number of these things. You know, it's at least Avogadro's numbers, 10 to the 23, right? If we had a small enough system, however, right, we could think of it as matter comes in discrete chunks, right? This would be atoms, right? Or molecules, okay? And so you think that the stuff that's making up this total mass, you know, I've got this stuff in a bucket, it weighs, you know, this many kilograms, and it's made up, if it was made up of just one thing, maybe it's methane gas or something like that, right? Then I can use the periodic table, I can look up methane, right? I know how much hydrogen weighs, I know how much carbon weighs, right? And I can figure out what one molecule of methane weighs. And that would be the discrete chunk size that mass comes in, right? Such that if I chopped a little bit off, right? When I had on my second, the last chop before it was all gone would be some unit of mass, right? And I can't chop that down further, easily anyways, right? And so that is true. But why it doesn't matter, and I'll show you. So let's think of a hydrogen atom, right? And we haven't done a lot of talking about the atomic hypothesis and stuff like that, but we've all taken chemistry, and so we know about atoms and stuff like that. And we probably remember that hydrogen is the simplest atom that there is. It's composed of a single proton and a single electron, right? The proton is positively charged, the electron is negatively charged. Therefore, as a whole, it's electrically neutral, okay? Because plus 1 minus 1 equals 0, right? But let's zoom in and let's just think of this, you know, positive charge and this negative charge. We're going to think of it in the old Bohr planetary model, where the electron we think of orbiting around the positively charged nucleus like the Earth does the sun, right? Not true, but you know, we can kind of think of it like that. And there's going to be some distance that separates them, right? We'll call that distance r, okay? We don't care about the direction of it. We're going to just stick to kind of a simple model here. And what I want to do is I want to compare, I want to look at this of course has a charge. I'm going to call it, I don't want to write that. There's a stand. I think we do it like this: E plus, and this is going to be E minus. This means this is, you know, one unit of charge, right? What an electron has a charge of, and what a proton has a charge of. Okay. Well, actually, let's just call it. It's going to be plus and minus 1. We'll say this is a charge of minus 1. This is a charge of plus 1. But we need to actually use. We need to use the actual units of how much. What is the value of this charge? So. That was a mistake. Let me just. All right. So I'll call this Q minus. I'm going to call this Q plus. Okay? Q minus is equal to minus 1.602 times 10 to the minus 19 coulombs. That's a really small number, huh? And then Q plus is equal to positive 1.602 times 10 to the minus 19 coulombs. So that's the value of that. Okay? We're also going to need masses and stuff, because what I want to do is I want to get the ratio of the electric force divided by the gravitational force, okay? So I'm going to need K, Q plus times Q minus over R squared, the distance that separates them squared, right? And then divide by the gravitational law, which will be like multiplying by R squared over big G, M1, M2, yes? And so you see that the R's are going to cancel, the R squareds cancel, okay? It's the same dependence on separation distance, right? And what I end up getting is something that's proportional to K over big G and Q plus times Q minus divided by M1 times, well, I'll call it M plus times M minus. That's probably a better way to write that, okay? So we need values for this stuff. So an electron was 9.1 is 9.1 times 10 to the minus 31 kilograms. M minus is, I think it's 1.6 times 10 to the minus 27 kilograms. Let me check that. I guess 6.7 to be more accurate. What else do we need? We need big G, which we probably remember from last semester, is 6.67 times 10 to the, I forget. Let me look it up here. Minus 11. Minus 11. And this is newtons meter squared per kilogram squared. Just to put the units in, okay? And then we had K, which we just got, which is 9 times 10 to the 9 newtons meter squared per Coulomb squared, okay? So if we plug all these values in, right, into this little formula here, right, then what do we get? And I'm not going to write the numbers in because I've already calculated it ahead of time, okay? But if we put these numbers in here, right, what do we get? We get that the ratio of the electric to gravitational force is, there it is, 2.27 times 10. Anyone want to take a wager on how much bigger the electric force is than the gravitational force? So think of it this way. If the gravitational force were 1, what would the electric force be? Right, that's what this ratio is telling us. I think it's 10 times bigger, 100 times bigger, 1,000 times bigger. Just give me a guess.
100 times bigger.
Oh, not even close. I already put times 10 to the something, right? So times 10 to the what? Times 10 to the 2? No. Times 10 to the 39. That's almost 40 orders of magnitude bigger, okay? So, you know, in this day and age, people love to talk about like quantum gravity, and it always amazes me because what the heck does gravity have to do with that size scale, right? It's so insignificant that it doesn't even make sense to be interested in pursuing it. So I think that's just nonsense. People do that, but some people think differently, and that's fine. They're allowed to think that. Maybe they're right. I don't know. But yes, on the small scale, right, gravity is so insignificant, right? I mean, 39 orders of magnitude, right? We could never, in the history of the future, right, ever accomplish a measurement with that much precision, okay? Right, maybe that's too strong a statement, but that's way too strong. I mean, that is, usually we throw things out whenever they're like an order of magnitude smaller, right? So, I mean, we can, you know, debate that, but yeah, 39 orders of magnitude smaller is very significant. So for this reason, right, the gravity matters for things like the sun and planets, and at least, you know, things like satellites and stuff, okay? Yeah, but the electric force is so strong, as you can see here, right, that it's significant on a small level. And so, in fact, it turns out that charge is quantized, meaning that it's made up of little bundles of charge that come in discrete little sizes, okay? And so that's what we're going to talk about next. All right, sorry to say I don't remember his first name. Millikan, he's one of the great experimentalists, American experimentalists, in fact, from the 20th century, did what is called the Millikan oil drop experiment, okay? And this thing up here, have you ever seen an old-fashioned perfume bottle? Like maybe in an old movie or something? The way that they would spritz themselves with perfume is they had a bulb which they could squeeze to blow air out, and a small tube that had a little hole, and it would force the perfume or whatever through this opening with the small holes in it, and we call it an atomizer. Okay, it's not really spitting out atoms, but it makes the particles very small. Old-fashioned engines that used carburetors had atomizers in them that would spread the fuel out in like a mist, so it would burn more efficiently, okay, inside the combustion chambers. So we have an atomizer here that spits out a spritz of oil, little oil drops, okay? And these oil drops will fall inside this, basically think of it as a big barrel, okay? It's going to be sealed off from the outside to avoid like air currents and stuff like that, so that the oil drops will fall a nice steady path, right? And they fall down through this device, and there's a metal plate that has a hole in it so that some of the oil droplets go through the hole and into this second area of the experiment, okay? In here we can shine a light at right angles to a little telescope that allows us to look inside the chamber, okay, and see the oil drops as they come down. So it's very dark inside, but when you shine that light in there, right, only the oil drop picks it up and scatters the light so it appears like a little star on a black background, so you see it very clearly, okay? Now the oil drop will fairly quickly reach what's called terminal velocity, and we talked about it, I think, last time, or last semester, though we probably didn't do any real detailed calculations with it. It's a little bit tricky, but you know, different things have different terminal velocity. So a small thing would reach a higher velocity because it has less wind resistance. Basically, where the wind resistance balances out with the gravitational attraction, and you from then on out travel at a constant speed as you descend. Okay. So at first, of course, these little oil droplets accelerate due to the acceleration due to gravity, but the air resistance inside the chamber causes them to reach terminal velocity, and so they fall with a constant velocity. Okay? And you can kind of say that it's proportional to its mass. And so you can determine the mass of the droplet, okay? Because really you're figuring out how big is the droplet. Is it, you know, a little round droplet like this, or is it a bigger droplet like this? They're nowhere near that big, a tiny little droplet. So I'm just showing you. So there's some different size in the droplet. That's going to affect its viscosity in the air, which will ultimately affect how much oil is in that little droplet. So it's the mass, okay? So you're going to calculate the mass of the droplet. Now, as the droplets fall through the air, just like when I was rubbing the amber on the silk, there's a triboelectric effect where it can pick up a little bit of charge, okay? And this metal plate with the hole in it that the droplet fell through, right, actually serves a couple of purposes. It's to, minimize the number of drops that we're looking at any one time, but also this electric plate, right, can be, you can run wires to it and hook it up to a battery and put a potential across it. Now, we haven't got to that aspect of electricity and magnetism yet, but if I charge this plate, if I put a battery here, right, and have a tunable voltage, so it's like your volume knob on a radio, right, so I turn the rheostat to the right, it's going to change the amount of voltage between the two plates. This creates an electric field, which acts on that charge and can bring it to a stop. Okay, and we can measure, excuse me, how much voltage we put on that, and that will help us determine how much charge is on there, okay? The details are not terribly important. I can kind of outline it roughly here. 1, measure mass of drop from terminal velocity. 2, adjust voltage, here's your voltage, until stationary, until you see the little star in your viewfinder stand still and stop moving, okay? 3, the charge on that oil droplet is going to be equal to the mass of the drop times little g, the acceleration due to gravity, times d is the distance it's falling here, d, divided by the voltage, okay? And then finally 4, repeat for many drops. Now this was a really labor-intensive experiment. You'd have to sit there for probably hours and hours. And oftentimes, Millikan would just play with like one drop, okay? He'd get a drop, and he would tune the voltage till he got it to stop. He'd record that value in his notebook. And then he had another element in here that I didn't draw because it's not necessarily necessary, but you can shoot X-rays into this. That charges the air. It allows the drop to pick up more charge. It can also remove charge from the drop. The drop will naturally lose charge from cosmic radiation, right, at various random times, right? And so he was able to like add or take away charge from the drop and record how the voltage changed. So he got the same drop as before, which is nice because he already, recorded what its mass was, and he can now calculate, or tune the voltage till he gets it to be stationary again and record that value, that voltage, that will give him that new amount of charge for that same drop as before, okay? You could, of course, do it just one drop at a time and then move on to the next drop, right? Or you could use X-rays or some other radiation source to put charge on the drop or take charge off the drop and do repeated measurements. So here's how you figure out the quantization of charge. Where does it come from? So this axis will be measurement, right? Measurement 1, 2, 3, 4, right? And on this axis, we're going to have charge. I'll use uppercase Q in coulombs, right? So this will be times 10 to the minus, minus 19 coulombs. And then get my scale right here. Start this at 1 down here. I'll put 2 here, 3, 4, 5, 6. How far do I have to go? One more maybe. Up to 7. Okay. All right, so each of these little dots that I've drawn is a new measurement, right? A recorded value for the amount of charge that he found on the drop, okay? And this dotted line that I've drawn is the average value of these nearby points, right? This may not be the sequence in which he measures them, but if you were to order them from smallest charge to highest charge and start at the bottom of the smallest charges first, right, then there can be some average value of these things that had around 2 times 10 to the minus 19 coulombs, right? And you can get this average value, right? So call it Q average here, right? And then you can do the same thing for this one. This is another average, right? For these points here. And then up here, we've got a couple of points with even more charge. They average, right? So where's the quantization of charge? It's the fact that these are discrete steps, okay? So this, right, is a step size, we'll call it E, our fundamental quantum of charge. That'll be the 1.6 times 10 to the minus 19 coulombs that I said was the charge of an electron, right? And then this would be 2E, for example, and we'd have tables with 3E and 4E and 5E, okay? And so that is why, that's how we figured out that it was quantized, right? The charge comes in discrete little bits, right, of 1.602 times 10 to the minus 19 coulombs. That's the charge of the electron. Okay, so charge is quantized. On the homework, you're going to have a problem where you've got values like this. I'll give you the actual numerical values, and you're going to be required to figure out what these spacings are. You have to average the similar data with a similar point. You have to make a graph like this, okay? I'm just going to give you a list of, measurement 1, charge was this. Measurement 2, charge was that. You have to assemble that data and make a graph like this and calculate what the quanta of the charge is, okay? So look back on this video in this section when you get to that problem. The last thing I'll mention is the demonstration from the beginning of the video, right? What was happening there? Okay, well, there's two things. With the leaves, right, in the electroscope, so these leaves in the electroscope in here, right, what was happening there is as follows. So if I draw my electroscope, it's got the wire coming in, then we've got the leaves like this, and we see that they're repelling. Up here on the top, we have some large surface, right, and then I have like a glass rod, for example, okay? If this glass rod is positively charged, as I said it was, right? I'll put 4 on there. That's going to cause the electrons in this metal, right, to be attracted to these positive charges as I move the rod closer, right? Through this electrostatic attraction that we talked about with Coulomb's law. That's going to cause negative charges, 4 of them in this case, to accumulate up on this upper surface. This is a metal. Metals are defined as these substances in which electrons flow freely. Okay? From a chemical point of view, they don't really participate in the metal-metal bonds next to each other, except in that they kind of share. It's almost like a supercovalent bond, if you can think of it that way. They share, each atom shares its electron or electrons with all of its neighbors, no matter how far away they are. So the electrons are free to move anywhere throughout the metal. Okay? And so the electrons from this aluminum foil will find its way up to this top surface to get as close to that glass rod as it can. Okay? Since electrons left from here, what happens? We get positive charges on these aluminum foil leaves. Okay? It's going to be equally distributed, right? You've got 2 leaves that both have positive charges, and they have a degree of freedom that allows them to move away from each other, so they're going to try to get far away. They're going to repel, you see? So that's fairly straightforward to understand, yes? If we did the same experiment with the bits of paper, what happens is, it's a little harder to explain, but if this is my glass rod, a little bigger this time because we're going to look at an atom. The paper is made of bits of, if there were no charge on here, right? Let me draw the atoms like this. It's a plus charge and then a minus going around it, right? So we've got the minus is the ring outside, the plus is like the center of the atom, right? Just going to put a bunch of atoms in here, right? If this glass rod, if it had no charges on it, then the atoms just stay like they are, right? They're neutral. The electron cloud that surrounds the nucleus of this atom, that makes up this, shard of paper, right, is not distorted in any way whatsoever. But if I brought some positive charges here, right, let's just do 2 of them this time, then the atoms closest to the rod are going to feel, their electrons are going to feel attracted towards that rod. And so this is going to change. And it's going to go from looking like this symmetric thing that I drew to this distorted look like this. You see that? It's kind of stretching out as much as it can. You see it? So it's creating what we call a dipole, okay? Or we're polarizing the material. So some materials are more easily polarized than others, and we'll talk about that when we talk about the dielectric later. But it's a property of materials. Some materials are very polarizable, and some are not, okay? And so because these negative charges have stretched out from their positive center quite a bit in this fashion, right, it's like it's negatively charged now, okay? And so it gets attracted to the rod. Now the distance dependence is a little bit different, but we're not going to get into that yet. And so that is what was going on with the demonstration at the beginning of the lesson. And I think that's all I have, other than giving you your homework and to remind you that I will put the solutions to the last problem set or homework assignment in a video, which will be labeled in a way that links it to the lesson that it was attached with. And I'll find some way to make those problem sets available online as well for viewers at home. But any questions? Anything you want to ask about before we cut? Okay. Then I guess that is it.